In the last tutorial, we reminded ourselves what a plasma is and how it is used in the lab. Then we looked at how plasma is used for surface etching, or for adding functional groups such as fluorine atoms to a surface, or for activating a surface for polymer grafting. Now we will look at plasma polymerization. Plasma polymerization is another method for the addition of certain functional groups onto a surface, like in surface treatment. However, it is different in the sense that the functional groups being added are all connected, as they are part of a polymer which is formed in situ and coats every single surface layer. This polymer coating is so thin, sometimes right down to the nanometer scale, which is 100,000 times thinner than the thickness of a piece of paper. Unlike in grafting, where it tends to be other polymers which you coat, plasma polymerization can be used to coat a huge variety of different materials, including everyday objects. Later, we will learn how some companies are using this method to provide an invisible layer of protection for mobile phones and clothes. But how does plasma polymerization work? The monomer, to be polymerized, is drawn from the monomer tube into the plasma chamber, under a vacuum. The coil generates radiofrequency radiation, which produces the plasma. Like in surface functionalization, electron impact causes fragmentation and excitation of the monomer. However, here, the excited monomers are capable of reacting with each other as well as the substrate to be coated. So a series of propagation steps occur, polymerizing the monomer as well as bonding them to every surface on the object. Plasma polymerization has been explored for over 100 years. However, this was with limited success due to the difficulties with controlling these mechanisms of polymerization and rearrangements, leading to polymers of very different chemical composition to the monomer. In the mid-1990s, an alternative method to using the plasma as a continuous wave was developed, which revolutionized the field of surface functionalization. Scientists discovered that using pulsed plasma, which is applying the electric field across the gas in microsecond pulses rather than continuously, led to much more controllable polymerization. This enabled them to make a polymer surface which was structurally more similar to the parent molecule compared to continuous wave plasma. This is because using pulsed plasma means there is less fragmentation of the monomers, as fragmentation and excitation occurs during the on periods. However, in the off periods, more conventional polymerization mechanisms can occur. The pulse timings can also be tailored for excitation of specific functional groups on the monomer, or for even the same functional groups which are in a slightly different chemical environment, making the process even more controllable. They started with polymerization of maleic anhydride, attaching anhydride functional groups on the surface. This is a very useful functional group to have present, as it is capable of undergoing a wide variety of reactions, to form many different surface coatings. Also, before, it was not possible to just polymerize maleic anhydride on its own by conventional methods. More recently, other polymers and molecules have been successfully coated onto surfaces as a result of plasma polymerisation, so it is a very versatile method of surface functionalisation. The technique of using pulsed plasma rather than continuous wave plasma has revolutionised the industry of surface treatments. So many companies are incorporating this technology into treating products. For example, polymerizing a fluorine-containing monomer onto the surface is another way of getting fluorine functionalization, which, as mentioned in the Power of Plasma Part 1 tutorial, can make surfaces with very low surface energies. This leads to super hydrophobic surfaces, which are so water resistant that water droplets will just roll off. The benefits of this type of invisible water repellent coating on mobile phones, microchips, and clothing is very clear. Also, incorporating perfluoroalkyl chains onto the surface leads to hydrophobic but also oleophobic behaviour, meaning that the surface not only repels water but also oil. This leads to huge potential applications in stain-resistant clothing and textiles, or to prevent corrosion and damage to boat hulls. In summary, we have looked at how plasma polymerisation can be used to add functionality to a large variety of objects and substrates, and how specifically pulsed plasma has rejuvenated the method, making it a very exciting topic within the multi-billion-pound surface coating industry. Tutorial. We reminded ourselves what a plasma is and how it is used.